Hi everyone and welcome back to my channel in Economist. So if you are someone who is following my Econometrics playlist, then you will know I have already covered what is classical linear regression model, and then I have started with the violations of the assumptions of classical linear regression model, where we have already covered what is heteroscedasticity, right? So that was the first violation of our CLRM assumption. Now, today we will start with something called autocorrelation, which is the second violation of the assumption of CLRM, right? And this is going to be our lecture number 15. So, what is the agenda for today's lecture? Here we will see with an example what is autocorrelation. We will understand the concept of this, and then we will go into the consequences. If autocorrelation is present in our linear regression model, then what will be the problem that might arise, right? So this is the agenda for today's video. Now let's start with the example. Here, this example depicts a scenario which is the stock market returns. We will consider the daily stock returns. Suppose you are considering some XYZ stock. Suppose we are considering some XYZ stock. It could be HDFC Bank, it could be Reliance, it could be Coal India, anything, any stock that you can think of. It is some stock, and we are observing the price or the return of that stock for 5 consecutive days, right? We are observing the return of this particular stock, XYZ stock, for 5 consecutive days. And what we see here is that the stock return on the first day is 0.5. On the second day, it increases to 0.6. In the third day, it again increases to 0.7. Fourth day, it again increases. Fifth day, it again increases. So this is a specific example where what we see is that in consecutive days, there is a strict increase. There is a sharp increase in the returns of the stock. So this is a particular example. Now, what do we understand from this kind of an example? Here, what we can do, we can name this stock return as a variable R, right? This is stock return is a variable R. Now, the first day return can be termed as R1. It is R2. Third day R3. Then it is R4. And this is R5. Now, what I do, I find out the covariance between R1 and R2. Right? I find out the covariance between R1 and R2. Now, can you pause the video and guess what will be this value? Covariance of R1 and R2. Here, I am not talking about any specific value, but what will be the sign? What will be the sign? Will it be positive or will it be negative? You can pause the video and think for yourself. And what you will see is that this value will be strictly greater than 0. Why this is greater than 0? See, this value, the value on the second day is strictly greater than the value of the first day. So here, the stock return is a kind of time series data where the value in the present day will be dependent on the value of the future period, value of some past period, right? The current price or the current stock return will be dependent on the stock return of some past year or past day or the previous day also, right? So today's value or today's stock return is not independent of the past value to the previous values, right? So that will give you a strictly positive covariance between R1 and R2. Now you can execute the similar exercise between R2 and R3. Then also you will see R2 and R3 will be strictly greater than 0. And this will be the same for all this year. R3 and R4, this will be greater than 0, and R4 and R5, here also you will see the covariance between these two years or these two dates will be strictly positive. Now, this is for this specific example. Now, what happens if I change this value a little bit? Suppose I change this value a little bit and I say that this value, this starts with 0.5, this is right, all right. But here you have suppose 0.2. In the second day, what you see is that the price or the returns of the stock drops to 0.2%. Then what will happen? Then if you find out the covariance, then this value will be strictly negative, right? This value will be strictly negative. And now if this again increases, then it will be positive. If this again falls, suppose it is 0.6, then it will be negative. So in this particular way, we can find out if the stock prices are dependent or not, and if they are dependent, what is the direction of the dependence. And now this exact same thing is depicted by autocorrelation. Here you see, I have found out the correlation on a single variable only. The variable is not changing. The variable is R only. I am just executing the covariance. I am just calculating the covariance on the values of the returns on different dates only. The date is different, but the variable that I am performing the covariance, it's not that R1 and R2 are two different variables. They are both the stock returns. They are both stock returns. They are on the same variable. Suppose I consider X and Y two different variables, then this is not autocorrelation because this is a different variable. This is also a different variable. But if I consider covariance of X1 and X2, then it will be X1. So X is the variable, X is a particular variable, and X1, X2 are two different values of that particular variable. Then it will be termed as autocorrelation. Auto means self. If you are finding out the covariance on a particular variable only, I hope you are getting the point, then this will be termed as autocorrelation, right? I hope this example will help you to understand the concept better. Now read this particular thing. If we compute the correlation between these returns and their previous day values, we may find a very high positive correlation. Now all these covariances are positive. If you take any two values, this will be positive because the stock prices or the returns are increasing over the time, right? They are increasing over the time. So you will see a high positive autocorrelation indicating the stock returns tends to move in the same direction over time, right? They are moving in the same direction. So basically it starts from a lower value and it's going to a higher value. The return in percentage are strictly increasing and we are getting a positively related stock returns, and hence we have a high positive autocorrelation. Now let us formally define what is autocorrelation then. Autocorrelation refers to the correlation of a time series with its own past value. So here this own word is very important. We are finding out the correlation with its own past values, right? This is autocorrelation. Now in regression analysis, what happens is that this variable, the variable here, as we consider the variable to be R. Now, in regression analysis, what we say, this variable is not the explanatory variable, but the residual or the error term, right? See here, read this paragraph. This is very important. It measures how the current values of a variable is related to its previous values. This is fine. Now, read this. In regression analysis, autocorrelation occurs when the residual or the errors are correlated with each other, violating the assumption of independence. So when I have discussed the assumption of CLRM model, we have said that covariance of epsilon t and epsilon say t prime, this should be 0 for all t not equals to t prime. So this is what is the CLRM assumption. But in case of autocorrelation, what happens? This is not equals to 0 mathematically. Mathematically, this is the error. This is also an error. The error is not changing, but we are calculating the error in two different time points. See, here the suffix is t and here the suffix is t prime. So if you consider the error in two different time points and you see that they are not independent. If you see they are not independent, that is they depend on each other. That is, this is not equals to 0, right? This is not equals to 0. Then you will say, yes, autocorrelation is present in our model. So in autocorrelation, what happens is that you are in case of regression, basically, in case of regression, what you see, not any explanatory variable, but the error that you have in your model, if they are related with each other, if they are dependent on each other, then this will mean that we are violating the assumption of independence and autocorrelation is present in our particular model, right? And why we are talking about time series data? Because autocorrelation problem is mostly prevalent in time series data. It is basically a problem of time series data, and heteroscedasticity is basically a problem of cross-sectional data. This I have already explained in some other video. I'll give the entire playlist in the description section. You can check the other videos out and you will understand that better, right? So see, in many situations, particularly with time series data, the assumption that the disturbance terms in the regression are mutually independent, this may not hold. In case of autocorrelation, this error terms are independent. This assumption is not holding. We are violating the CLRM assumption and we say autocorrelation is present, right? I hope this concept is clear. If you have any doubts in the concept, you can let me know in the comment section, right? Okay. Now let's move on and see what could be the possible types of autocorrelation. There are three possible types. As I have told you, there could be positive autocorrelation, negative autocorrelation, or no autocorrelation. So if the past values are positively influencing the future values, as is the case we have seen in the example. For example, the stock returns tend to follow the trends. If the stock returns is increasing and it is increasing gradually over the time, then what will happen? The covariance between epsilon t and epsilon, say, t prime, this will be strictly positive. And this will give you the positive autocorrelation. Now, if the past values are negatively influencing the future value, then there will be negative autocorrelation, which means this covariance will be strictly negative. And if there is no autocorrelation, then the past values will have no systematic influence on the future value. So in our particular example, if this is zero point 0.5, this is also zero point 0.5, this is also zero point 0.5, this is also zero point 0.5, and this is also zero point 0.5. So the past values have no systematic influence on the future values, right? If this is the situation, then we will say that no autocorrelation is present in our particular model, which is the required assumption of CLRM, right? So this was the type of autocorrelation. Now the final thing that we will cover is what could be the consequences. What could be the possible consequences of autocorrelation? So see, the first consequence would be that bias, standard error, and inefficient estimate. So we'll derive the consistency and inefficiency in the future video. In the next video only, we'll derive all the consequence as we always do. But as of now, I'll just give you the overview of what will be the problems that would arise if autocorrelation is present. So under autocorrelation, the problem is the estimators will be unbiased. This is not an issue. This will be unbiased. They will be consistent. Consistency is also not an issue. But the problem is it will be inefficient. It will be inefficient, right? This is the problem. This is the same problem that we have faced in heteroscedasticity, if you remember. The estimators are unbiased, the estimators are consistent, and they are inefficient. Inefficiency is the main problem that leads to other problems as well. If the estimators are inefficient, which means the variance is inflated. The variance is not what it should be, right? The variance is not minimum. In any regression model, we want the variance to be minimum, but it is not so here. So the estimators will be inefficient. See here, the presence of autocorrelation does not make the OLS estimators biased. So unbiasedness property will hold. We will see this, we will derive this in the next video. But it does make them inefficient. So inefficiency will be there. And then this means that the OLS estimates may not have the best possible estimate, that is, they will not be blue. This is the same consequence as we had in heteroscedasticity. And if this inefficiency is not holding, which means variance will be inflated, which means standard errors cannot be estimated properly because standard error is just the square root of variance. So standard errors can also be underestimated or overestimated. They will not be correctly estimated, leading to unreliable confidence interval and hypothesis testing. For example, see this scenario. Imagine estimating the impact of inflation on the stock prices. If we want to do that using this OLS regression, and suppose in our model autocorrelation exists, then what will happen? The estimated standard error will be too small, making insignificant variables appear significant, right? So standard errors will not be properly estimated. If variance is too high or too low, anything is either the case, it's not rightly estimated, then standard errors will also be not rightly estimated, which will make our variables may look significant or may look insignificant in the wrong direction, right? So this will be the first consequence, that inefficiency problem will be there. So our standard errors will be biased, and this will lead to many more problems that we see in the next point. See, if the standard error is not validated, then what will happen? The hypothesis testing will not be valid. And t-test, f-test, chi-square test, any kind of test that you perform will not give you right results. So all these tests are invalid if autocorrelation is present in your model. So see this, that since standard errors are miscalculated, the t-test, f-test all will be unreliable, leading to incorrect conclusions about statistical significance. And the next point, you may incorrectly reject a true null hypothesis, which is the type 1 error. We can commit type 1 error, or we can fail to reject false hypothesis, which leads to type 2 error. So the chances of committing type 1 and type 2 error is very prevalent if autocorrelation is present. For example, see this, that if a model analyzing GDP growth and the government spending exhibits autocorrelation, if you want to measure that if government spending is boosting GDP growth or not, and you fit a model and you see autocorrelation is present, then what will happen? It may falsely suggest that government spending significantly impacts GDP when it is not, right? These problems may arise. So we'll see in the fifth point that policy issues will also appear, economic policy issues will also appear. So this could be a point in that as well, that we are assuming that government spending is, positively affecting the GDP growth. Our model also shows that, but the autocorrelation problem makes it invalid, right? So due to autocorrelation problem, our the model will be, the variance will be inflated. As a result, the hypothesis testing will not be valid. So this kind of problems will arise. Also, if the model is not properly estimated, forecasting also cannot be done properly. Autocorrelation indicates that information from the past periods is not fully captured, making the model less effective at forecasting. If a model fails to account for autocorrelation, predictions will have high variance and low accuracy. So if the fit of the model is not good, if you use that model to forecast anything, that forecasting will also be invalid. For example, in stock market analysis, failing to address autocorrelation may result in highly volatile and inaccurate stock price predictions. So in stock market, this phenomena is more vividly seen. Like if you are using a incorrect model, if you are working with an incorrect model, you fit that incorrect model and find out forecast. In case of suppose stock market price analysis, then you will see that price will be either very inflated or it will be very different from what it actually is. So this kind of problems may arise. Also, the R square and the adjusted R square will be inflated. They will be artificially inflated. Autocorrelation can artificially inflate the R square values, making a model appear to have a better fit than it actually does. So this happens because the dependent variable values are correlated over time, creating an illusion of explanatory power. Actually, the explanatory power is not there, but it will create, autocorrelation will create an illusion that the explanatory power is there, and that will artificially inflate our R square and adjusted R square, which we do not want. So this is also another severe consequence of autocorrelation. For example, see, a regression model predicting inflation rates may show a very high R square due to autocorrelation, misleading the analyst into believing a model is highly predictive when it is not. Right? If R square is very high, we will think that yes, the model is very good, it's predicting very well. But actually, it's a case of autocorrelation where the analyst will derive misleading conclusions out of that. So this is another problem. And the final problem is the inefficiency in the policy analysis and economic analysis, that many economic models relies on regression analysis to guide the policy decisions. If autocorrelation exists and it is ignored, right? If it is present in your model but it is ignored, then it will lead to poor policy recommendations based on statistical inference. Since hypothesis testing itself is invalid, any conclusion that you derive from the model will not be efficient. For example, if the government uses a model with autocorrelation to decide fiscal policy, it might implement ineffective tax policies based on misleading results. So these are the 5 consequences of autocorrelation. They are exactly the same as heteroscedasticity. Unbiasedness, consistency holds, but inefficient estimate, and rest of the things will follow from the inefficient estimate. If the variance is not right, then the standard error cannot be right. If the standard error is not right, then hypothesis testing is not valid. If hypothesis testing is not valid, then predictions and forecasts that you draw from the model is not right, and that will lead to inefficiency in the policy making aspect, right? So this is the entire thing. And the final thing, the final question that we want to figure out is how to fix this autocorrelation. So we have already understood what could happen if autocorrelation is present in our model. But the question is how to fix that. There are several methods that you can fix. So these are the 4 methods. See, what could be the solutions? First is that we can transform the data. Since we are talking about time series data, we can take first differencing all log transformation. That will sometimes help you to eliminate patterns in time series data. Or you can use the generalized least square method or weighted least square method. I have shown you the process in case of heteroscedasticity. I'll also show you for this autocorrelation purpose. So this method will adjust for autocorrelation, improve efficiency. Also, there is some specific test that you can perform, Cochrane-Orcutt procedure. This is a statistical test that is specifically designed to handle autocorrelation. Also, we can use the robust standard error. So in heteroscedasticity, I have shown you how to do that. Techniques like hack, that is heteroscedastic and autocorrelation, consistent standard errors will help you to adjust autocorrelation. But one thing that is missing in the list is that what we will, discuss in details in the later on some video is the Darwin-Watson test. This process is not mentioned in this list, and I feel that this is the test that we frequently use, and you should know how to perform this test in much more details. So I'll be deriving everything around, about this Darwin-Watson test probably in the next video or in some subsequent video, right? So stay tuned for that. And this is all from my side for today. I hope you like this video and you get some useful content out of this. If you like this video, give me a thumbs up and do subscribe to this channel, AN Economist. And this gives me immense motivation to continue making such useful videos. And if you have any doubts anywhere, if you want to know something more, if you want me to elaborate on some point, you can ask me so in the comment section. And let's meet you in the next video where I will be deriving the consequences, and I will also be explaining what is Darwin-Watson test in details, right? So stay tuned and let's see you in the next video. Thank you for your time.